Lecture 11, the design of columns. Columns are structural members which are designed to carry predominantly compressive stresses. They consist of a concrete part and a steel part to form the reinforced concrete. Columns transmit the applied load from each floor level and transmit all the collected loads to the foundation. And finally, the foundation transmits all these loads to the ground. Columns can be classified in various ways. We can classify columns by cross-section, for example, rectangular columns or circular columns. We could classify columns by the position of the applied load, say concentrically loaded columns or eccentrically loaded columns. We could classify columns by lateral support, either braced columns, which now in the Eurocode is referred to as non-sway columns, or unbraced columns, which in the Eurocode is now referred to as sway columns. We could classify columns by the effective length. We could have short columns, which is now referred to as non-slender columns in Eurocode, and we could have slender columns. The primary difference between non-slender and slender columns is that slender columns primarily fail by buckling, while non-slender columns fail by crushing. In braced columns, or rather unbraced columns, the column is mostly freestanding. It doesn't get its lateral support from any other support or any other member, whereas in braced columns, the columns get some lateral support from another member, such as a shear wall or a support that can take up the horizontal actions. In all this, the most important sort of classification between columns is still whether it is slender or non-slender. Then further to that, we have to classify slender and non-slender columns with whether they are braced or unbraced. In this lecture, we'll only look at non-slender braced columns. Since the effective length is also usually quite critical, we look at this structure, which is the Milimani Low Courts in Nairobi, Kenya. You can find that some additional beams have been put at this point. You may wonder what these beams are for, yet there is no slab here. So one of the reasons that may require this is so that we reduce the effective height or the buckling length of this column, because the longer the column is, the more likely it is to buckle. In the design of columns, we usually use design charts which have one key critical that changes, which is the ratio of D2 over H. And in these graphs, we have on the y-axis, we have the axial load N over BHFCK, and on the x-axis, we have M, which is the moment applied over BH squared FCK. In the next chart, we will see how the D2 over H changes. So from 0.05 to the next one, which will be D2 over H, is now 0.10. Then we still have N over BH FCK on the y-axis and M over BH squared on the x-axis. Same goes on for the next chart from D2 over H is equals to 0.15 all the way to D2 over H is equals to 0.25. The y-axis remains the same and the x-axis remains the same. We will be using these charts to finally get our ASFYK over BHFCK from these charts. We'll do an example later to see this. The effective height of columns is also quite important and is dependent on the end conditions. We'll have an end condition at the top and an end condition at the bottom that will affect the effective height. So from a question we could get off the clear height, then we would need these factors to get the effective height. So two items, there's a clear height and there is an effective height. So condition 1 is where we have full fixity. Condition 2, we have partial fixity. And condition 3, we have nominal restraint. And this, of course, will affect the effective length. This is a simplified way of achieving the effective height from the clear height, but in essence, you could calculate this. Calculate the effective height using the stiffnesses of the adjacent members. For this lecture, we'll stick just to this, and this could be considered for your further reading. This is similar to what you will have covered in our strength of material course, where I will have to find K, or the buckling length of different struts will be affected by the end conditions, whether it was pinned, on the top and the bottom, whether it was fixed, whether one side was pinned or one side was fixed, whether it was just a cantilever with one side fixed and this other side free. So depending on the end conditions, that will affect our buckling length. Let's do an example. So a braced rectangular column with a cross-section dimension of 300 millimeters by 400 millimeters, and the concrete grade is C3037, carries an ultimate limit state axial load of 1100 kilonewton meter and a maximum bending moment of 185 kilonewton meter. ULS stands for ultimate limit state. So in short, what that means is that these loads have already been factored by the partial factor for actions. So this is already factored. Determine the reinforcement required. The column has a clear height of 2,765 millimeters and supports shallow beams at the top and has deep beams at the bottom. The column is non-slender. so it will probably fail by crashing. Assume a cover of 30 millimeters, 8 millimeter stirrups, and 25 millimeter main bar. The yield strength of steel is 500 MPa. So we need to calculate D2, which is the distance from the edge of the column to the center of the reinforcement. So to do that, we will calculate the cover plus the diameter of the link, or in this case, also called the stirrups, plus half the main bar diameter. So that will give us 50.5. We'll then get B from the question and H from the question as well. B is usually the smaller dimension and H is always the larger dimension. And D we get from the question 1100 kilonewtons, and M we get from the question as well as 185. The yield strength of steel is 500 MPa, and this we'll expect to be using H bars for our reinforcement. You'll need to read off the condition at the top and at the bottom. So we are told at the top it has shallow beams. So if we can remember, shallow beams will have, say, partial fixity. So full fixity will have deep beams, partial fixity, shallow beams. And for nominal restraint, you'll have something like pad foundation, causing nominal restraint. In our case, the condition at the top is that it has shallow beams which offer partial fixity. So we'll come and read off that column. That's the column we're interested. And deep beams at the bottom. Deep beams offer full fixity. So that gives us condition 1. So that's the row we'll now be interested in. And we'll have to read off the section where the two coincide. So our coefficient in this case will be 0.8. So to get the effective height from the clear height, we'll multiply 0.8 multiplied by the clear height, which we had been given here. And we'll get the effective height is 2,213 millimeters. Something very important in the design of columns is called eccentricity, because it contributes an additional moment to the moments already experienced in the column. I'll give a small analogy of the effect of eccentricity. So, assuming you are this person carrying 50 kg in scenario A or 40 kg in scenario B, you'll find that even though 50 kilograms is a heavier load, carrying it in scenario A will be easier than in scenario B because of balance. Here it's more balanced, so this could end up being easier than carrying a 40 kg on one side, because there will now be an imbalance. So same thing happens in columns. We'll want to consider this in the design of columns, whether there is an eccentricity. So when we design columns, we usually have the axial load which we total from each floor, and when we want to design the column at this section, instead of considering maximum load on span A and span B, we will consider span A with the maximum load and span B on this with the minimum load, and experience shows that this combination is usually much worse because now we have an additional imbalance created. So this scenario is the one which we will use to design that column. When we do this combination of maximum load on one span and minimum on the other, then that gives us the highest moment. So this, of course, is a function of balance. To cater for eccentricity, then, we have three conditions that will be provided in your handout. One is h over 30, two is the effective length over 400, or three, 20 millimeters, just given to you. So in our case, h, which was the larger dimension of the cross section, because we had a 300 by 400 cross section, so h is 400, we divide by 30 to get 13 millimeters. The effective height is 2213 over 400, 5.5, and 3 is 20 millimeters. So to get the additional bending moment, we pick the greatest of these three, which in our case happens to be 20 millimeters, and we multiply this greatest eccentricity with the applied axial load. To get an additional moment. So in our case, 22 kilonewton meter. The total bending moment in this case then will be 185 kilonewton meter plus 22 kilonewton meter to get 207 kilonewton meter. And our N, which was 1100 kilonewtons, was already given. We then get the chart to use. So we will need D2 over H, which we had already calculated, as D2 was 50.5 and H 400, the larger dimension of the cross section. So that gives us 0.13, but the charts are in multiples of 5. So you can go ahead and be conservative and use the chart above this and find that D2 over H is 0.15. We'll then calculate N over BH of CK, which is 1100 kilonewtons, which comes out as 1100 times 10 to power 3 newtons over 300 millimeters multiplied by 400 millimeters times the characteristic strength of concrete, which is 0.306. Then we'll get M over BH squared FCK, which will be 207 kilonewton meters, or 207 times 10 to power 6 newton millimeter over 300 times 400 squared times 30 to get that. Then we'll go to our chart. So of course we decided on D2 over H equals 0.15 to be conservative, since our actual value was D2 over H is equals to 0.13. So N over BH of CK will give us 0.306. So we draw a horizontal above that point, and M over BH squared FCK will give us 0.144. So we read off a value just above that point, which gives us the value at that point where the two lines intersect somewhere. You can plot a point and read off the value. So that value that we read off, so in our case, will be about 0.3 will be this value. So AS F1K over BH FCK is 0.3. We could rearrange this to get the area of steel as a subject. We compute the figures to get area of steel required is 2160 millimeters squared. Then we'll need to compare this with the minimum allowable in the code. In our case is 0.1 NED over 0.87 FYK. This is provided to you in the handout. We'll find that the nominal area of steel we require for this column is 253. And since the area of steel required is greater than the minimum, then we provide for the area of steel that is required, which was 2160 millimeters squared. We'll go back to table 1 and read off a value that gives us 2160 millimeters squared. Because we are providing for the area of steel for all bars in one go, it's not like in beams where we provide for bottom then top. Ideally, the minimum number of bars we could select here will be 4, because we can't have 3 bars in a cross section. We can't have 3. It's always good to have a minimum of 4 in a rectangular section. In our case, we could have 4H32. That will give us 3216 millimeters squared. We can also have 8H20. That will give us 2513. There are many more nuances in selecting this. You can choose one of the many that you find. It's always good to be symmetrical. So choose either 4, 6, 8, and so on. Choose even numbers so that you can have a symmetrical bar arrangement. So in our case, if we had 4H32, I'll have 4 bars. And that will give us 4H32, 2513 millimeters squared. Or if you went ahead and selected 8H20, and you will have 1, 2, 3, 4, 5, 6, 7, 8. Now this will have 8H20, which gives us 2513 millimeters squared. Of course, you choose one of these, so let's go with the first one here for the next step. So some knowledge you may have is that when we compress something in the longitudinal direction, by the law of conservation of mass, we expect that it will expand laterally. So this is known as the Poisson's effect. And to cater for this, we need to provide for links or stirrups to cater for that. So to do that, it seems I went with 8H20. So if we go with 8H20, then we'll take, to get the stirrup size, we'll go with a quarter times the main bar diameter, which was 20, to get 5 millimeters. However, for the steel provided or available in Kenya, for example, the smallest diameter you could have is 8. So you have H8 stirrups. For the vertical spacing, there are 3 conditions provided to you in the code. You could have 20 times the main bar diameter. You could select the least column dimension, since we had a 300 by 400 cross section, and 300, or we just pick 400. So from these 3 conditions, you pick the lowest, which happens to be 300. So you adopt a 300 spacing, so provide H8 at 300. This could also be the point where you sketch. So if you have a cross section, we went ahead with 8H20, so we had 1, 2, 3, 4, 5, 6, 7, 8. That was 8H20, gave us 25. Then we'll need our stirrups. You can use a different color. It's just a bar that ties up all the reinforcement, and this will have H8 at 300. So that will be our solution. Let's try a second example. An unslender axially loaded reinforced concrete column with a clear height of 3.2 and a section dimension of 500 by 500 is to be designed to carry an ultimate axial load of 4,000 kilonewtons. It supports some deep beams at the top and a pad foundation at the bottom. The concrete specified for use is C2530. Provide the main steel reinforcement and stirrups. Assume a cover of 40. 25 main bars, 8 mm stirrups, and the characteristic strength of rebar is 460. Since it's 460, you can go back to T. So we need to calculate D2, which is the distance between the center of the reinforcement and the edge of the concrete column. In our case, we have already been given the cover as 40, the diameter of the stirrups as 8, and 25 millimeters is the main bar diameter. We use that assumption to start off our calculation. Calculate B, or rather read it off from the equation, which is 500, and H is also 500. We'll then calculate or read off the axial load, which has already been factored, so 4,000 kilonewtons. There is no moment given, so we'll assume that as 0 to begin with, and the characteristic strength of rebar is 460. We also need the end conditions at the top and at the bottom. So in our case, we have deep beams at the top So that's usually full fixity. On the top we have full fixity, so we'll be interested in that column. And at the bottom we have a pad foundation, which gives us condition 3. Now the two intersect will be our value for beta. So the effective height is 0.9 times 3200, which gives us 2880 millimeters. We had converted the clear height 3.2 meters to millimeters, which gives us 3200. Get the nominal eccentricity. We'll have our three conditions: h over 30, effective height over 400, and just 20. When we compute this, we get 16.7, 7.2, and 20 millimeters. We pick the largest of these three, which is 20 millimeters, and we multiply the axial load times the largest eccentricity to get the additional bending moment as 80. So our final total bending moment, since we had not been provided, will just be 0 plus 80 to get 80 kilonewton meter. So N is 4000 kilonewtons and M is 80 kilonewton meter. To figure out which design chart we will use, we will need D2 over H, which in our case was 60.5 over 500 to get 0.121. To be conservative, we can go ahead and choose D2 over H is equals to 0.15. And then for our charts, calculate N over BH FCK, get 0.64, and M over BH squared FCK to get 0.0256. We go to the charts. Conservatively, we'll use D2 over H is 0.15. We'll have our N over BH squared 0.64. We'll draw a horizontal line about 0.64. M over BH squared FCK was 0.0256. We'll draw a line about that. And where the two intersect on the green spot, we'll read off our value of AS FYK over BH FCK. So in our case, if this is 0, this is 0.1, and this is 0.2, AS FYK over BH FCK is closer to 0.2 than 0.1. It's not exactly on the line, so we could estimate that being 0.18. You'll work that out and rearrange to make AS the subject, which will be given as that, and we'll find the area of steel as 2446 millimeters squared. Then we'll compute as mean, which is 0.1 NED over 0.87 FYK. That will give us 1000 millimeters squared. Then we'll compare the area of steel required versus the nominal area of steel, and we'll get the area of steel required is greater, so provide for AS required. So from our table 1, we'll have various options. We'll have 4032, that will give us this area of steel. We'll also have 8020, that gives us 25 13 millimeters squared. You could also have 6 T25. It gives us 29 45 millimeters squared. Usually work with one, and whichever answer you go on with, make sure you remain consistent. You could provide a sketch at this point, or you could go ahead and compute. In our case, let's assume we went with 8 T20 again. So to get the stirrup size, it's just a quarter times the main bar diameter. So if it was 80/20, that will give us a quarter times 20 to give us 5. So we provide T8 stirrups. For vertical spacing, we'll have 3 conditions: 20 times the main bar diameter, least column dimension, or just 400. So in our case, it will be 20 times 20, 400. Our least column dimension is 500, since the column dimensions were 500 by 500 or 400. So in this case, the least is just 400. So you could go ahead and provide T8 at 400 spacing. Then at this point, you will provide a sketch. This is your column, and you had 8 bars. And a stirrup. I'm gonna tweak this. This will be T8 at 400, and this will be 80/20, which gives us 25 13 millimeters squared. So that's how you'll provide the area of steel for a column, and that's the end of the lecture. See you in the next one.